Okay, section 14.4 has to do with reaction rates and temperature and activation energy. Really, there's a lot more to it even than that, but that's what it's called, reaction rates and temperature, activation energy. And to start with, we're going to introduce a new idea to you, that is reaction coordinate diagrams. So reaction coordinate diagrams are a way to map out how the energy of the system changes over the course of a reaction. And so usually you'll have as the x-axis some form of energy, either internal energy or enthalpy or Gibbs energy. In this case we're going to look at enthalpy. And then on the x-axis you have the reaction coordinate. So Rxn COORd. And the reaction coordinate can be kind of complex. It can, for example, represent a bond angle or a bond length if the reaction involves the breaking or twisting of bonds or things. But I think the easiest way to think about the reaction coordinate is like, imagine you're watching a movie of two reactants colliding and breaking and forming bonds and the products leaving, like a little microscopic movie of the process of a reaction. Well, the x-axis here is just the frame number. Like, you know, if you want to go back and watch the exciting part on YouTube, you'll drag it back here. So this is just the progress bar, or the frame number for the movie, which shows a reaction proceeding. And so how does the energy change over the course of a reaction? Well, you'll start at some value here. So this is the enthalpy of your reactants. And then it's going to require, it'll always require some amount of energy to initiate the reaction. Most reactions involve taking stable chemicals and breaking some bonds in order to form new bonds. And so when you're halfway through that process, you've broken the old bonds, but you haven't formed new bonds yet. And so you're at this maximum of energy. It requires some energy to even get that process started. And so the difference in energy between reactants and that maximum point is called the energy of activation, or the activation energy. This top point up here, sometimes represented with a double dagger, is called the transition state. And you know, it's neither reactants nor products. It's whatever they look like when they're in the middle of breaking the old bonds and forming the new bonds, nothing has quite settled down into its final configurations yet. So that is the transition state. And here we'll have products at the end. And the difference in energy between reactants and products, well, that's just the enthalpy of reaction. And so here a reaction coordinate diagram tells the story about how energy shifts as you go through the course of the reaction. So we can see that some reactions are endothermic. This blue one has products that end at a higher energy than the reactants. And some reactions are exothermic. The red one here shows the enthalpy for products lower than for reactants. But they're all going to have some change in enthalpy. And if you have a reversible reaction, then the activation energy for the forward reaction is what we've shown here. But if you have a reverse reaction, then products can go to reactants as well. Right? So for an endothermic reversible reaction, the products will have an easier time reaching that transition state in the reverse direction. And so the activation energy for the reverse direction will be different, and it will be lower than the activation energy for the forward direction. For reversible reactions that are exothermic, it's the opposite. The products will have a more difficult time achieving that transition state. Now we can look at the reaction coordinate diagram for this particular reaction. Take two nitrogen monoxide molecules. They're going to collide and react in order to form nitrogen and oxygen. And you can see here in the transition state, the oxygen-nitrogen bonds have begun to break, and the oxygen bond and the nitrogen bond, they have begun to form, but they haven't, neither of those processes are quite complete. And by definition, the transition state is just wherever the energy happens to be at a maximum. Now, we can start to talk about reaction rates from a microscopic perspective using collision theory. You know, some reactions proceed rapidly, some reactions proceed slowly. Can we come up with a theory that considers the microscopic properties of the reactants and is able to quantitatively, or in other words mathematically, explain the reason for the different reaction rates and predict how the reaction rate might change in response to temperature? And the answer is yes, we can. That is collision theory. So collision theory explains reactions in terms of collisions between reactant molecules. And not every collision between the reactant molecules is going to lead to a reaction, and so there are a lot of factors to consider. The first factor is just the collision rate. Right, so this is part of the reason why higher temperatures lead to faster reactions, because higher temperatures have molecules moving around more rapidly and they collide, they encounter one another more frequently. Every collision is an opportunity for the reaction to proceed. But that's not the only factor. So not all collisions have enough energy to overcome that transition energy barrier. So if you have two molecules and they're both traveling the same direction, but this one's a little faster and they just barely kiss one another and bounce off, technically they've collided. But there wasn't very much energy in that collision. You need to have sufficient energy to reach that transition state in order to roll over to the other side to products. And so only some small fraction of the collisions is actually going to be energetic enough to proceed. And then lastly, 3 is sterics, which is a new word. The sterics refers to how the orientation of the molecules needs to be appropriate for forming and breaking new bonds. They don't just collide. Molecules have atoms in particular locations, and certain bonds need to break or certain bonds need to form. And so some reactions, maybe it's not that big a deal. Most collisions will be in an appropriate orientation to cause a reaction. The other reactions, maybe they need to collide just right. They need to collide such that they perfectly fit together in order to have the reaction proceed. So here we have figure 14.16, looking at that same nitrogen monoxide reaction. And you can see if they collide You see me? There we go. If they collide sort of side by side like we see at the top, then the orientation is right for these oxygens on the left to begin to form a triple bond, for the nitrogens on the right to begin to form, oh, I'm backwards, sorry. The nitrogens on the left form the triple bond. The oxygens on the right form the double bond. But if the nitrogen monoxides collide, say, in this T-bone fashion, then the oxygens cannot form a new bond and the reaction cannot proceed properly. Or if they collide sort of in reverse like this, well then neither of them can form any new bonds. And so that's a collision, even if it's very energetic. It's not going to lead to the proper reaction. So if we look at this hypochlorite, actually that's not charged, sorry, it's just chlorine monoxide with an oxygen atom producing a chlorine atom and oxygen. What sorts of orientations are going to lead to this reaction? Well, you're going to need to have the oxygen atom colliding with the chlorine monoxide molecule on the oxygen side in order to form that new oxygen-oxygen double bond. If it collides on the chlorine side, then it's not going to form products no matter what. So this is all called sterics, steric constraints, steric factors. You'll talk a lot about sterics in organic chemistry because it's an important thing to consider when you're trying to synthesize your organic products. And then the effect of temperature on kinetic energy. We've seen a plot like this several times now where molecules at a given temperature are not all traveling at the same velocity. There is a distribution of velocities called a Maxwell-Boltzmann distribution. And some of them are going very fast and some of them are going very slow, and most of them are here kind of in the middle. So if you consider that you need some certain threshold of kinetic energy in order to overcome that activation energy barrier, then only some fraction of the molecules are capable of undergoing a reaction. And when you increase the temperature, say from the blue curve to this red curve, the distribution shifts such that a higher fraction of the molecules at high temperatures are going to have that sufficiently high kinetic energy. Okay, so all of these considerations are summarized in an equation. Collision theory is basically summarized in the Arrhenius equation. And the Arrhenius equation is an equation to give us the value of K, that rate constant. K is going to equal A times E raised to the power of negative energy of activation over RT. And so A here is going to be called the frequency factor. So the frequency factor includes the rate of collisions as well as the fraction of those collisions which lead to a reaction due to steric considerations. So if you have a reaction that is very sterically constrained, then A will be small. If you have a reaction that like almost every collision leads to a reaction, then A will be larger. So it kind of depends on what types of bonds are being broken versus being formed. If bonds are only being broken, then more collisions are likely to lead to a reaction because the orientation isn't quite as important. And then this is the energy of activation. Then RT here, the kinetic energy is equal to RT, the average kinetic energy of gas molecules is equal to RT. And this R is going to be the, I want to make sure I get it right, 8.314 joules per mole Kelvin. And so the temperature needs to be expressed in units of Kelvin. This is the same quantity as the gas constant 0.08206 liters atmospheres per mole Kelvin. This is the gas constant. We're just expressing it in different units, in joules per mole Kelvin instead of liters atmospheres per mole Kelvin. And the reason we do that is because it needs to cancel out with the activation energy, which will be expressed in joules per mole or in kilojoules per mole, and we'll need to make sure that those units match up. So this term overall is called the, let's see, does Boltzmann have two N's? It does. The Boltzmann factor. The Boltzmann factor and the frequency factor, or sometimes it's called the pre-exponential factor. So we can use the Arrhenius equation to get some really interesting information about reactions. Okay. What we want to do is take the Arrhenius equation and get rid of this exponent. Oh, sorry, one quick point. This Boltzmann factor, the e raised to the power of negative EA over RT, this is the fraction of molecules at a given temperature which will have the activation energy or greater. So that's what this form looks like. As the temperature increases, this will approach 1, and as the temperature goes down, this will approach 0. And it's kind of bounded, you know, between 0, meaning none of the molecules have sufficient energy, and 1, meaning 100% or all of the molecules have enough energy at, you know, as temperature approaches infinity. Okay, so if I want to get rid of the exponent, then I'll take the natural log of both sides. And so I'll get the natural log of K is equal to, and now there's a product of two things in here, so I can change that into the natural log of A plus the natural log of e to the negative EA over RT. But if I take the natural log of something that is an exponent, those undo one another. The natural log is the inverse operator for exponentiation, and so this becomes plus a negative EA over RT. So why is this better for us? Well, let's try to turn this into a linear form. Chemists are obsessed with lines because then we can take a lot of data and we can use a best fit line to extract important parameters from our data. So let's let y equal the ln of k, and we'll let x equal 1 over the temperature. When we do that, then we'll have ln of k is y, and we'll have the natural log of A is going to be a constant B, and then negative EA over R is going to be M, and 1 over T is going to be our X. So B is going to equal the natural log of A, and M, our slope, is going to equal negative EA over R. And 1 over T is X. So in other words, here we have Y is equal to B plus MX. Y is equal to MX plus B. Okay, so in other words, what you'll do is collect a lot of data. You'll take the find the rate constant over a range of different temperatures, and you'll plot the natural log of that rate constant against the inverse temperature. And you'll get a lot of points when you plot them like that. And when you fit them to a line, the slope is equal to negative EA over R. And the intercept is equal to the natural log of A. So these parameters, the frequency factor and the energy of activation, they seem really abstract at first. You wouldn't really know how to experimentally determine how many times a second the particles are colliding and things like that. You cannot measure the energy of the transition state because it only exists instantaneously. It's not something that you can capture and study. And so how do you get the frequency factor and the activation energy? Well, this equation tells you how. So we can rearrange the Arrhenius equation. This form of it is nice if you have lots of data points and you can use Excel to get a best fit slope. But there's one more form in case you don't have a spreadsheet program handy. And this is just the 2-point form of the equation. The natural log of K1 over K2 is equal to energy of activation over R times 1 over T2 minus 1 over T1. So this is the 2-point form of that equation. And you'll notice we don't have a negative in front of the EA anymore. Well, that's because we've kind of reversed the 1 over T1 minus 1 over T2 became a 1 over T2 minus 1 over T1. And this is the way that your book presents it. So that's how I'm going to show it to you. So you'll measure the reaction rate and get a rate constant at 2 or more temperatures. Put the values in here, and then you can find your energy of activation. And then you can go and find your frequency factor by going back to that earlier form of the Arrhenius equation with your energy of activation and solve for the natural log of A. So let's look at some real data. Again, this is different. Here we have dinitrogen monoxide reacting to form nitrogen and oxygen. We've measured the rate constant at 2 different temperatures, well, at 4 different temperatures. We only really need 2 of them. So let's pick the 2 that are furthest apart, and let's just start putting values in here. So 850 Kelvin will be our T1 and our K1. T1 is 850 Kelvin, and K1 is 0.0018, 0.0018. And then T2 will be 1120 Kelvin. 1120 Kelvin, 850 Kelvin, and K2 is going to be 9.75. And those are what? Inverse molar, inverse seconds. That, by the way, tells you that it is a second order reaction. And then what's the value for R? 8.314 joules per mole Kelvin. Okay, now we have everything we need to solve for that activation energy. Oh, hold up. Sorry, my calculator wasn't booted up quite yet. All right, so let's first take the natural log, and I know I'm typing log instead of ln, but this is a natural log. The natural log of 0.0018 divided by 9.75. Okay, and then I'll multiply that by 8.314, and then I will divide that by 1 divided by 1120 minus 1 divided by 850. And as long as you're careful like that, you can just plug it in your calculator in one step. And I got an activation energy of 252,000 joules per mole. So EA 252,000 joules per mole, or in other words, 252 kilojoules per mole. That is the energy of activation. And now we can go back and find the frequency factor, because we know that the natural log of K is equal to the natural log of A. Well, actually, let's just do it this way. This is even better. We'll say that K is equal to A times e to the negative EA over RT. And we can solve for A in this form. So we will take, let's take the value of K at that higher temperature. So that's 9.75, 9.75. We will divide that by the negative activation energy divided by E raised to the power of the negative activation energy divided by R 8.314 times T 1120. I think I've got that in there correctly. And so here we have a frequency factor A equal to 5.53, and I'm honestly going to struggle to count the number of digits there. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, times 10 to the 12th. And if that seems like a really large number, just think how many times a second are these particles actually colliding with each other? Well, maybe they're colliding with each other billions of times a second. They are teeny tiny particles after all. Okay, and that's it for 14.4.